Hello, welcome to our optimization presentation. We are going to talk to you today about an evtol superhighway. I am Adam Kagi and my group project associates are...
I am Munibun Billah.
And I am Coulton Karch.
And we'd like to stress that our project scope cannot be fully summarized in this 10-minute presentation and encourage you to speak to one of the three of us about our efforts in detail. To provide this project with a little bit more context, the use of evtol, or electric vertical takeoff and landing vehicles, for the transport of goods is common today. However, hiring drone operators can be expensive. There isn't really a good reason why this process shouldn't be automated. And if this process is then automated, it can be optimized. We decided to apply this optimization specifically to the Utah area. We live here and data was plentiful and very available, and so we decided to separate the state into regions. That will be explained in a little bit more detail later, and then using this mapping we were able to find lots of useful information for drone applications.
For our project, we actually have two optimizations. One is in the small scale, that's the object avoidance anti-collision software that we developed. The other optimization is the large scale highways in the sky that we also developed. Highways in the sky are required for this problem because of the infrastructure required in the design. LTE towers are required so that the UAVs can communicate with each other in order to avoid each other. So cell towers need to be created along the route. As well, radar needs to be included on the route to prevent bad actors. Potentially, UAVs, as they are small and hard to detect, could cause destruction along different places in the state. And so to limit and regulate this, radar and bistatic radar specifically would be needed to detect these. Also, charging stations on the route could be implemented. This would also be another reason to include highway design. And finally, because range is limited, these charging stations would be required.
Our optimization revolves around Euclidean distance. That is our overall function, which can be seen in the formula on this slide. Since one objective can only be truly optimized at a time, the x-coordinate is the one that we've used as our design variables, and the y-coordinate is one that's set at equal steps between the initial and start points. And so with our constraints, the optimization will generate a path around buildings so that drones will avoid static objects. This part of the optimization is applied to small scale, and so it will take place between one UAV and its surroundings. The UAV will then try to move back to its original path.
For the project, we use the dataset provided by the Utah government. This dataset contains all kinds of information that we can think of about Utah, and the figure contains all of the building locations in Utah, and it has 1.3 million buildings in the dataset. And since it's a really large dataset, we had to do some kind of optimization to how to go through the data, and we use dynamic programming and recursion to make our algorithm run faster. And also the data set was provided as the centroid for the buildings, so we had to convert them to x and y coordinate to measure the distance and make it a map.
This is the result of our collision software. We were able to avoid the large obstacle in the path and travel between the 2 points without issue. The circle represents a static object. We at this time have not yet done a dynamic object.
So we used k nearest neighbor to cluster the buildings from the Utah to divide them into suitable delivery zones. And we can see the delivery zones in the figure. And for those, we used all 1.3 million buildings provided by the dataset. And we have used Euclidean distance as a metric of distance and 1,000 neighbors to calculate the distance from each building to cluster them together. And we can see some of the clusters in the figure, and some of them have been overlaid by the buildings. And in the figures, the x and y coordinates are in meters.
To further optimize our data set, we take the zones here pictured in blue and we draw edges between them and use the minimum spanning tree to find the least number of edges and thus the least number of paths needed to get to each node. This provides our highways in the sky. These edges and highways are 50 kilometers in range, which is reasonable for a larger commercial UAV, as would be carrying these larger shipments of goods between these areas. And this uses the 10,000 buildings randomly selected to generate these zones that we'll be traveling to. The larger data set is infeasible for the larger number of buildings that we have.
Okay, another aspect of this project is to divide the zones into two categories. One is to have a small area where we will deliver the goods using a small range UAV that like those have 5 kilometer range, and we'll connect those smaller range using using the UAVs that has larger range, let's say for 50 kilometer range we have used before. And we can see from the figure that we can connect all of the buildings or nodes in a zip code using a 5 kilometer range UAV, and we can use those drones to deliver our product. And we can also see that there is one lone building in this zip code that is outside of our range, and so unfortunately we cannot deliver the product using the range of that our EOV.
The impact of this project is rather broad. On one hand, there are many applications for a detailed Cartesian coordinate map of a geographical area. So the database and data processing that was used can be applied to many data sets that exist from United States governments or other data collected by other governing bodies, and that on its own is very useful. On the other hand, in terms of evtol superhighway, nothing like what we've done has been done to the level it has been done for Utah in the past, and the kind of basis for superhighway structure has really been developed here, and that is very applicable and very, very relevant and impactful. Further research and investigation into this topic could include the ideas that the current optimization only factors in static objects, and there are more dynamic objects that UAVs could have to avoid, as well as while carrying capacity is taken into account to kind of a basic level, it's not flight time is not optimized to the best of its ability. And another big thing is that elevation is not taken into account by this optimization. It's purely two-dimensional, and fast routes between 2 points can be found using changes in elevation as well.